Welcome back to our class. Let's continue our discussion for the key technical challenges to optical communication in the next decade. In the previous chapters, we have discussed the first two key changes and challenges in the optical communication field over the next decade. That is, how to achieve ultra-high speeds and how to expand the spectrum of optical communications. Our research in these two directions is aimed at achieving large bandwidth and large capacity of backbone optical networks. However, in the case of backbone optical networks, in addition to continuous capacity expansion, it is also very important to maintain long-distance transmission. The transmission distance of optical communication is mainly limited by a medium of optical communication, that is, the optical fiber. The attenuation of optical fibers determines the transmission distance of optical communication to a great extent. Today, in this part, let's move on to the evolution chain of optical fibers. Optical fibers standard are defined by ITU-T, including G.651 to G.657. G.651 is a multi-mode optical fiber, and G.652 to G.657 are single-mode optical fibers. Multi-mode optical fibers are used for short-distance communication, while single-mode optical fibers are used for long-distance communication. In this chapter, we will talk about single-mode fibers only. G.652 optical fibers are the most widely used optical fibers. At present, G.652 optical fibers are used for long-distance and metro networks, except for drop optical fibers from fiber to the home scenario. G.652 fiber, also called the dispersion unshifted single-mode fiber. It is also the 1310 nanometer best performance fiber. It has zero dispersion at 1310 nanometers. At the 1550 nanometer window, this is used by the DWDM technology. It has a dispersion of about 17 picoseconds per nanometer per kilometer. For DWDM systems, this large dispersion actually limits the transmission distance without any electrical regeneration. In order to reduce the influence of dispersion on optical communication system, a single-mode fiber with a dispersion coefficient of 0 at 1550 nanometer is developed. This fiber is called G.653. However, a fiber with a dispersion of 0 can easily cause nonlinear effects like four-wavelength mix. The nonlinear effect is not good for the DWDM system. We will introduce the nonlinear effect in the next chapter. So as a result, G.653 optical fibers were soon obsolete. Instead, another fiber, the G.655 optical fiber, has the minimum attenuation near the wavelength of 1550 nanometer, and the dispersion is also small, but it's not zero. Therefore, the G.655 optical fiber can be used in the WDM system. Later, with the maturity of dispersion compensation technologies and the development of coherent optical communication technologies, this coherent optical communication technology can provide large dispersion tolerance. The fiber dispersion is no longer a major factor. It is no longer the limitation for the system transmission distance. Instead, the main contradiction becomes nonlinearity or signal-to-noise ratio. Therefore, the G.652 with large modulus length and diameter is more suitable for DWDM networks. Hence, except for a few maintenance projects, G.655 optical fibers and cables are no longer built. In addition to these three, G.654 is an ultra-low loss optical fiber with the lowest loss around 1550 nanometer window. Currently, G.654 is a high-price optical fiber, and it is mainly used in non-relay submarine optical cable communication systems. When we need a long distance for the transmission, we can use G.654. Also, it can meet the requirement for those high attenuation span. And the last one, G.657 fiber, it's the most widely used fiber except the G.652. G.657 fiber is used in the fiber to the home job cable scenario. G.652 fibers now are mainly used in long-distance backbone optical network, such as SDH and WDM coherent networks. G.652 fibers are still widely used because they have certain dispersion and can suppress the nonlinear effect. The G.653 fiber has been phased out because of the nonlinear effect is severe due to zero dispersion, and G.655 fibers have no advantage over G.652 fibers. So G.655 fibers only occupy a small proportion on the live network. As the long-distance transmission rate of the future backbone optical network increases continuously, the optical fiber technology also needs to evolve to meet the deployment requirements for the 400 gig or even higher high-speed and large capacity systems. Some new optical fibers must be used to effectively improve the optical signal-noise ratio and extend the transmission distance. Currently, the research on new fiber technologies mainly focuses on three types: the large effective area fiber (ULAF), low loss fiber (LL), and ultra low loss fiber (ULL). The core material of the low loss optical fiber is germanium doped silicon dioxide, which is the same as that of the G.652 optical fiber. The typical loss is 0.185 decibel per kilometer by optimizing the manufacturing process. The ultra-low loss optical fiber improves the refractive index and manufacturing process of the optical fiber. It does not dope germanium in the core layer, thereby further reducing the optical fiber loss. Large effective area single mode fiber has the advantages of low loss and ultra low loss fiber technology by increasing the diameter of the mode field of the fiber and adjusting the refractive index difference to achieve large effective area. And also it has the advantages of low loss and suppressing the nonlinear effect of the fiber. So currently, the typical loss of ultra-low loss fibers can be reduced as low as to 0.17 decibel per kilometer. The optical fiber loss with a large effective area can be reduced to less than 0.16 decibel per kilometer now. The three types of optical fibers we mentioned above are still developing, and there are two main development chains. First, the optical fiber attenuation is further reduced. With the continuous improvement of preform manufacturing technology and wire drawing technology, the optical fiber attenuation can be reduced to less than 0.16 decibel per kilometer. The lower the fiber attenuation, the lower the span loss, the higher the OSNR, and the longer the transmission distance. Secondly, the cost of optical fibers is further optimized. Currently, the cost of ultra-low loss optical fibers is 3 or 4 times higher than common G.652 optical fibers because they use the pure silicon fiber core technology. The cost and price of the ultra-low loss fiber will decrease as the process improves, the supplier increases, and the production scale expands. These fibers, including traditional G.652, G.655, low loss fibers, ultra low loss fibers, and large effective area fibers, they have some common advantages, namely relatively low loss. Currently, the existing technology can achieve 0.14 decibel per kilometer, and the price is relatively low. In addition, the splicing operation is simple and the loss is also low. However, We should also know that for future optical network evolution, these existing fibers still have many disadvantages, such as large dispersion, strong nonlinear effect, and poor transmission speed. Right now, the optical communication industry has noticed these problems, so it continues to explore in other directions. The first major research area is small mode multi-core fiber. A common single mode fiber consists of a core and cladding around it, while a so-called multiple core fiber consists of multiple identical cores in the same cladding and arranged in a certain shape. When optical signals are transmitted through multiple cores, a transmission capacity of this multi-core optical fiber is equivalent to a transmission capacity of several conventional single-core optical fibers. Compared with single-core, single-mode optical fibers, the multi-core optical fibers can increase the transmission capacity without increasing the installation space and cost of the optical cables. Currently, space division multiplexing transmission experiments have achieved a total transmission capacity up to 10.16 pbits per second in a small mode multi-core fiber. Another research direction is the hollow fiber. At present, some domestic and foreign companies and university research institutes are developing a new type of air-core optical fiber. That is, light is transmitted in the air in the optical fiber. Theoretically, this type of fiber has no fiber core. This can reduce the attenuation, increase the communication distance, prevent the interference caused by the dispersion, and also support more frequency bands. In addition, it allows strong optical power injection. It is estimated that the communication capability of this fiber is even 100 times of the current fiber. Right now, these two types of fibers still have technical difficulties. For example, like the coupling, signal amplification, and splicing. This will be the key research direction in the next phase. Lastly, let's make a brief summary. In this chapter, we discussed the history of optical fiber in optical communication from G.652 to G.653 and then to G.655. I also share with you two main directions of the current fiber research. In the first direction, on the basis of current optical fibers, we will continue to make efforts in manufacturing processes to reduce loss and nonlinear effects. For example, low-loss optical fibers, ultra-low-loss optical fibers, and large area optical fibers. These are the evolution direction in the short term. The second direction is to adopt new optical fiber structures. For example, small mode multi-core optical fibers and also the air core hollow core optical fibers. These two solutions can increase the transmission capacity to the order of pbits, and they are oriented towards medium and long-term evolution. That's what we have covered in this section. Next, let's use two questions to consolidate the content of this section. First, it's a single choice question. Which of the following types of fibers has a dispersion coefficient of 0 at 1310 nanometer? A. G.652, B. G.653, C. G.654, D. G.655. We mentioned this topic when introducing G.652 fibers. The dispersion coefficient of G.652, it is 0 at 1310 nanometer window. A is the correct answer. The second question, it is a multi-choice question. Which of the following are the advantages of single-mode optical fibers? A. Low loss as low as 0.14 dB per kilometer. B. Splicing is simple, easy, and it will cause low loss. C. The price is low. D. The transmission speed equals to Volcom light speed divided by 1.45. As we mentioned earlier, single-mode fiber loss is relatively low. The splicing operation is simple and the price is low. But relatively speaking, its transfer speed is the weakness. It's only about 2/3 of the speed in the light. So the D option is not correct. The correct answer is A, B, C. Well, that's all for this chapter. Thank you.